So the other day we discussed about how the entropy factor changes. Even if it comes to chemical reaction, how does it change? Now, what if I have a chemical reaction happening in a system like A is reacting with B, giving C and D, and all of them are of different states, let's say. One is gaseous, liquid, and all of that. In that case, how do we calculate what is the total entropy change of the reaction? Entropy change of the reaction. In that case, we can write as uh, since as per thermodynamics third law, we can calculate the absolute entropy. We can calculate the absolute entropy of C, D, B, and A in their respective states, and that can be multiplied with the C to identify what is the total entropy of C on the right hand side and D on the right hand side. And generally, whenever we write about any state functions parameter in a chemical reaction, it's always about the product's value minus the reactant's value. And product's value is C into entropy of C plus D into entropy of D minus A into entropy of A plus B into entropy of B. So that would be summation of NiSP minus summation of NiSR, products minus reactants. Correct? So this is how we can calculate delta S of the reaction. Everyone got that? Now notice delta S of the surroundings, on the other hand, will be how much amount of heat that has been given to the system in a negative value. So minus Q reaction by T. Okay. And Q reaction can be written as minus delta H of the reaction by T. Okay. So this is how we can write the delta S of the surroundings, and this is the delta S of the reaction, which is nothing but system. And you can notice that if the delta H of the reaction is negative, surrounding will be positive. If delta H is positive, surrounding will be negative. Correct? I suppose this part is clear to everyone. Yeah. Now, before going further into the details of more reaction based entropy calculations, let me introduce one more important term, that is about spontaneity within the process or the chemical reaction. Whenever we talk about a spontaneous reaction or any changes that are occurring spontaneously, we learn that they are all irreversible. And if there is any irreversible change, it will always increase the entropy of the universe as per second law of thermodynamics. Okay. So I can say that delta S of total is greater than 0 implies that it is a spontaneous change. And by formula, we can write delta S of total is equal to system plus surroundings. And system plus surroundings has to be greater than 0. Surrounding, as I told you, can be written as minus Q by T. And if you're operating at constant pressure, Q will be equal to delta H. So I can replace this Q with delta H. So minus delta H by T. And at constant pressure, I can write delta S of the system minus delta S of the surrounding can be written as minus delta H of the system by T, and both should be greater than 0. Now, if I multiply T on both the sides, so I'll get T into delta S of the system minus delta H of the system, that is greater than 0. So if I multiply minus on both sides, so I'll get delta H of the system minus T delta S of the system is less than 0. Got it? This is what I'll get. Now, this is where I'll define it as a new parameter. This is what we define as a new parameter, that is delta G. Delta G of a system is less than 0. This factor is what I'm defining it as delta G of the system. So delta G of a system, if it is less than 0, we can call that as the change in free energy of the system. So change in free energy of the system, if it is less than 0, that means we are doing a spontaneous change, or that means there is a spontaneous change occurring. G represents the Gibbs free energy. It is a state function and it is a system driven parameter. So it has nothing to do with surrounding. As long as systems information is known to you, you can figure it out. Okay, so from here we can say for any spontaneous process, delta S of the total has to be greater than 0, or we can write delta G of the system has to be less than 0. But delta G of the system has to be maintained at constant temperature and pressure. So as long as you are maintaining at constant temperature and pressure, we can say this factor is less than 0 is correct. Clear, everybody? Okay. Now let me tell you how do we define. Let me tell you what. How do we define the free energy in general? In general, free energy is always defined as H minus Ts. H is the enthalpy or the total heat content of the system. Minus Ts is called as the stored energy. And G represents whatever be the work done by the available energy. So free energy is the energy which can be converted into work. In simple terms, remember it this way. Free energy is the energy which can be converted into work. Okay. I often quote this example while, to make you understand in a simple way. Imagine this, everybody. Suppose today I decided that from tomorrow onwards I'll do, jogging in the morning. Got it? And when I measured the total amount of enthalpy in my body, that means everything that is present in my body, if at all I convert that into heat, how much energy I can have. Let's say I calculated that and I find that I can be able to, I'll be around, let's say I have 20,000 calories in total. The total heat content in my body is 20,000 calories. Okay, correct. Now, out of this 20,000 calories, if at all I start, let's say jogging tomorrow, and let's say it's a continuous process, I keep on jogging. And what is the amount of energy which I can utilized for jogging? That means jogging is a work which I have to do, correct? So to do that or to perform that work, how much amount of energy I can do? Can I convert the entire 20,000 into work? That is impossible. Okay, because I have to maintain a body structure also. If at all I have to maintain a body structure, I need to have some stored energy also in the body. Got it? So let's say the stored energy, the minimum amount of energy to keep my structure and my entire body working, functioning, for that, let us say 5,000 calories is essential. Out of the 20,000, 5,000 calories is essential, which means how many calories I can burn and convert that into work? Around 15,000, isn't it? And this 15,000 is free energy. Clear, everybody? So, in every system, in every chemical, every substance, there is a certain, slab of enthalpy it has. And out of that slab of enthalpy, some amount of energy is minimum required to sustain itself. And the rest of the energy, the differential energy, can be converted into work. Okay, that's how the basic definition has come across. So G is equal to H minus Ts. Notice H being enthalpy or the total heat content, Ts is the stored energy, G is the work done available. Now, what if I operate this at, constant temperature and pressure? So that means if there is any change in free energy, it has to be delta H minus delta of Ts. And if you are maintaining it at a constant temperature, it will become T delta S. And this delta G at constant temperature and pressure, if you notice this value here, and this value becomes less than 0, then we can say it is a spontaneous change. Isn't it? Then it is a spontaneous change, or if it is a chemical reaction, we say it is a spontaneous chemical reaction. And that's what I'm trying to analyze it here. You can see that delta G is equal to delta H minus T delta S. So from there I can say if delta H is being negative and delta S is also being negative of the system, then when will this delta G will be positive or negative? You can see if you are maintaining at a high temperature, it is coming as positive, which means it is non-spontaneous. But if you're maintaining at low temperature, it might become spontaneous. And if delta H is negative, S is positive, and if you go towards high temperature or low temperature, it does not matter. It will always be spontaneous. So this is a best condition for spontaneity. So this is a direct statement that is being usually asked. What is the best conditions for spontaneity of the reaction or for a change of the system? What is the best condition, everybody? It has to be an exothermic change as well as increase in the entropy. These two are more favorable conditions for for spontaneity. Okay, next one. If delta H is positive and delta S is also positive, then the positive higher temperature value helps to make it spontaneous. Lower temperature makes it non-spontaneous. And lastly, the most unfavorable condition for spontaneity is what, having endothermic change at the same time having a negative entropy change. Then it is always going to be non-spontaneous change. Everybody, please look into his the definition of delta g and how it is being defined for spontaneity. Okay, go through it quickly, then we'll go ahead. Okay, now before going ahead and understanding how the entropy change happens in every substance possible, let me just quickly tell you. Suppose if we have any chemical reaction here, let me write down that here itself. Okay, for a chemical reaction, like A plus B is giving C plus D. This kind of chemical reaction is there. And here we have SA naught, SB naught, SC naught, and SD naught as the absolute entropies, correct? And these are all measured at constant temperature and pressure when they are measured. Okay. And obviously naught represents these are all per mole. Okay. The entropy was measured at per mole unit. Then I can know that delta S of the reaction will be equal to, okay, C times of SC naught plus D times of SD naught, and that minus uh, A times of SA naught plus B times of SB naught. This is what you will have. And now here I can put those factors. If P is constant at a constant pressure, if T is equal to T1, clear? And from T1 it is changing to T2. Then what is the formula? Delta S delta S naught 2. That means how much amount of change in the reaction. I can write it as delta S naught 2 is equal to delta S naught 1 plus delta Cp of the reaction, into ln T2 by T1. This is the formula I can use. Now, delta Cp of the reaction is same way how we have written above. C into Cm of C plus D into Cp, sorry, Cp of C plus D into Cp of D, that minus uh, A into Cp of A plus B into Cp of B. This is how we can calculate delta Cp of the reaction. And this is the formula you can utilize for change in entropy from temperature T1 to T2. Okay. This is delta S2 of the reaction. Similarly, if T is constant, if temperature is constant, okay, and pressure is changing from P1 to P2, if at all pressure is changing, correct? Instead of temperature, no, pressure is changing. Then what will be the formula? Then it will be delta S naught 2 will be equal to delta S naught 1 plus, instead of delta Cp, now you will have delta NGR into ln P1 by P2. ln P1 by P2. Okay. So we can directly remember it this way. So how we can get it as delta S2 and how we can get it as delta S2 at constant pressure and constant temperature. Okay. Everybody understood? Another thing what you need to uh, help yourself, correct, is graphical representation. So a lot of graphical questions can also come in from this area, where graphical representation of temperature and entropy. Graphical representation. So if you notice the graphical representation here, so usually if you have temperature versus the entropy, okay, what is that exactly giving us? See, suppose if at all I have area under this graph here, let's say this is how it is given, and I'm talking about area under this graph. So area under this graph means at a constant temperature, some ds is changing, and that you are integrating, isn't it? So this area A will be equal to T into ds and integral, isn't it? This is how we write down T integral ds, maybe from S1 to S2. So if it is from S1 to S2, this is what you will write, correct? Imagine what is this exactly giving us? Isn't it what exactly the heat is? We know that this is how it is defined. ds is equal to dq reversible by T. So dq reversible, if at all you integrate this from 0 to q, that will be equal to T into ds S1 to, sorry, integral T ds S1 to S2. So basically what we are getting is the heat actually. So the area under the curve between T and S, if you plot, you'll always get what is the amount of heat that is being supplied to the system. So that is Q reversible is what I'll get. So Q reversible is equal to integral T ds S1 to S2. Or another way of writing is delta S will be equal to integral dq reversible by T, T1 to T2. Okay. This is another way of writing it. But as much as a graph is concerned, this is how you can decode that. Okay. Now in this case, if you notice, if you have an temperature increasing but entropy is constant, if entropy is constant, that means ds is constant. What is the q reversible? That has to be 0. So that means if you notice at this position here, if I write it as a graph for T and S, you should be able to describe about the process also. Let's say here, if this is how I have written it, clear, these 4 lines, starting from, let's say here, A to B to C to D. This is how I have written it. So what am I exactly getting? A to B is an isothermal process. B to C is a reversible adiabatic process, because reversible adiabatic process entropy does not change. And this one is also isothermal process. This one is also reversible adiabatic process. And to be precise, A to B is actually isothermal expansion. Isothermal expansion. And B to C is reversible adiabatic expansion, because in expansion only temperature will decrease. C to D, C to D is basically isothermal compression. It is isothermal compression. And D to A is reversible adiabatic compression, which is nothing. It is implying the Carnot cycle, isn't it? This is what we discussed in Carnot cycle. So P versus V, you're starting with this A to B, B to C, C to D, and from D to A. So this is the Carnot cycle we are talking about. A, B, C, D. So when pressure versus volume graph is like this, that can be converted into temperature versus entropy graph this way. Okay. Now in a cyclic process, you know that the area between A to B, this area is the Q in, right? This is the heat that has been coming inside. And C to D is the area which is Q out. correct? Because here is the heat that is being thrown out. So this is the area in and out. So if I remove the in and out, what will be the area under this graph, beta? So if this is the area in and this is the area out, in that case, now the area under this graph will be only the work done, isn't it? That will be the reversible value, which is in a cyclic structure, that will be the work done, because delta U is anyway 0. So the total heat that has been given to the system will be equal to the work done. Okay. So I hope you guys understood what I'm trying to say. Okay. So here, let me write down this way. This is the heat given, QH, from the hard body. This is the heat going out, QC. This is the heat given and heat out. Okay. So eta will be equal to Q heat given plus Q out divided by Q heat given. This is how the practical efficiency was established. Clear, everybody? Right. This would be very much useful. The graphical knowledge will be very much useful to calculate the efficiency. So this kind of questions will be often given. So learn it how to use that. Okay. I'll do some of the questions which are related to it. But to be honest, the questions related to efficiency are most asked in physics. Okay. So here it is mostly about, uh, you know, uh, calculation of entropy and free energy. This is what we are more concerned about. Right. Now, just like that, what if I have to calculate the, now we learned how to calculate enthalpy. We learned how to calculate entropy. Now let us calculate free energy also. Free energy of a chemical reaction. Okay. So let me put that calculation of delta G of the reaction. Delta G of the reaction. For a chemical reaction, where you have A plus B giving C plus D. Then let's say this is delta G naught F formation of A. Okay. Gives free formation value of A, delta G naught formation value of B, delta G naught formation value of C, and delta G naught formation value of D. In that case, delta G naught of the reaction will be equal to C times of delta G naught formation of C plus D times of delta G naught formation of D, that minus A times of delta G naught formation of A plus B times of delta G naught formation of B. This is what we know, delta G of the reaction, how we can write it down. Okay. Clear? We can do the same thing in terms of delta H also. That means delta G naught of the reaction can also be written as delta H naught of the reaction minus T delta S naught of the reaction. So even if these parameters are given, you can use the same value here and calculate. That is delta G naught of the reaction. Clear? If temperature is changing or if pressure is changing, in that case, how do we calculate? So check out. At constant pressure, and temperature changing from T1 to T2, in that case, delta H of the reaction will be equal to, okay, delta H naught 1. Okay, that means this is at some standard temperature. Whenever I'm using it as 1, which means it is at standard temperature, correct? That plus delta Cp of the reaction, into delta T. Delta T is T2 minus T1. This is how we can write down delta G of the reaction. Okay. And delta S of the reaction, this also I told you already. Delta S of the reaction is equal to delta S naught 1 plus delta Cp of the reaction into ln T2 by T1. ln T2 by T1. Okay. So these two can be individually calculated and then substituted back into this equation to get delta G naught of the reaction. If these terms were not given, if these terms are not given, if only delta H, delta S terms are given, you use that, substitute the values here and calculate. Okay. I guess this part is clear, everybody. I'll make you do a lot of questions, don't worry. So first understand the theory part. Okay. So then I'll show you how exactly it can be utilized in various questions. Now, one thing that should come to your mind is, sir, how did we get this equation and this equation? We are directly using it, you know, for the calculation purpose. But is there any derivation for that? Yes, indeed. So let me show you the derivation for this one, because this I have written it earlier already. I'll directly show you that. Okay. So let me take you back to Kirchhoff's law. What is Kirchhoff's law? And that's where I have derived that equation. Just before the second law, I have written it there. Here. See. Suppose there is a reaction here. A plus 2B is giving C. You can take any reaction, it doesn't matter. A plus B plus C plus, giving C plus D, and you can do it in any different forms. That's still fine. Now, when it comes to chemical reaction here, suppose there is some amount of uh, delta H of the reaction change due to temperature. Okay, I am saying, imagine this reaction happening at temperature T1 first, and then again I'm doing at temperature T2 second time. So when you're performing same reaction at two different temperatures, you might have a difference in the enthalpy. And let me write this small difference of enthalpy of delta H of the reaction. And delta H of the reaction can be written as small change due to temperature. There is a small change in enthalpy of C minus small change in enthalpy of A minus 2 times of small enthalpy of B, correct? Because products minus reactants is always the delta H of the reaction. So this is what I have written. Now let me recall, any small change in the enthalpy can be represented as Cp into dt. That's the definition. Cp is equal to delta H by dt. This is the definition per mole, correct? So therefore, if there is any small change in the enthalpy of C due to temperature change, I can represent it as Cp of C into dt minus Cp of A into dt minus 2 times of Cp of B into dt, correct? So now if I take dt common, so what do I get? Cp of C minus Cp of A minus 2 times of Cp of B. This is Cp of B. And this is what I'm writing it as delta Cp of the reaction. This is what we have represented there as delta Cp of the reaction. That into dt. Okay. Now if I integrate them at two different temperatures, delta H1 being the value at temperature T1 and delta H2 is the enthalpy change of value at T2. Then I can write it as delta H2 minus delta H1 is equal to delta Cp of the reaction. Consider this delta Cp is not, or it is constant and it is independent of temperature. Then I can write delta Cp outside and integrate dt. dt will be integrated to d2 minus t1. And this is how we got that value. So delta H of the reaction at temperature T2, and this is delta H of the reaction at temperature T1. That is equal to delta Cp of the reaction into T2 minus T1. Everybody understood how we got that? Kirchhoff's law is very well applied in the case of ionization and electron gain enthalpy. Let me explain you how. Okay. There are two terms which you will often come across. Okay, whenever we discuss about ionization in periodic properties, if you remember, we discussed the term ionization energy and ionization enthalpy. How is this two different? See, whenever we use the word energy, by default we are setting that temperature at which we are calculating is 0 kelvins. Understood? So we are assuming that at 0 kelvins, what is the energy that it is possessing or requiring? Okay. So whenever I use the word ionization energy, back of my mind is that I'm operating at temperature 0 kelvins. At 0 kelvins, if a metal is releasing out an electron to become M plus, then the amount of energy required is called as ionization energy. Okay. And have you noticed something? This is a monoatomic species. This is also a monoatomic species. And electron can also be assumed like a monoatomic species. It is like a particle. And what is the Cp value for monoatomic species? Phi r by 2, phi r by 2, and phi r by 2, correct? So in that case, what will be the Cp of the reaction? Products minus the reactants. So that will be phi r by 2. Now, delta H2 minus delta H1 is equal to delta Cp into delta T. This is what we learned. So delta H2 minus delta H1 is equal to phi r by 2 into T2 minus T1. So delta H1 is equal to ionization at 0 kelvins and IP, ionization potential, okay, or ionization enthalpy, that is equal to ionization energy plus phi r by 2 into T2 minus T1. And T1 is 0 kelvins. So therefore, this is the formula I'll get. IE1. IE1 is that the energy required at 0 kelvins, and IE ionization potential or ionization enthalpy is equal to IE1 plus phi R T2 by 2. Or simply, I can write it as any temperature T by 2. From here, what can I conclude, everybody? Check out the conclusion here. Conclusion is, if you're operating, if you're trying to extract an electron from an atom at a higher temperature, do we require more energy or do we require less energy to extract an or to release the electron out of it? We definitely require more energy, isn't it? So therefore, delta, as temperature increases, ionization potential required to remove an electron, to remove an electron from an isolated atom, from an isolated atom increases. Done. This is the conclusion what you can. I guess this part is clear. Done. How the Kirchhoff's equation or Kirchhoff's law to express the delta H values is useful in the case of ionization enthalpy. Okay. Similarly, the second application is electron gain enthalpy. Okay. You know that electron gain enthalpy can also be expressed as electron affinity. But remember, electron affinity is a term that must be used only when you are at 0 kelvins. So if it is at 0 kelvins, we often use it as electron affinity. And one thing you know that electron affinity is a negative delta H electron gain enthalpy is a negative value of electron affinity. So therefore, if I use a Kirchhoff's law, what exactly is happening here? You see now the as per reaction here, an element is taking an electron to become M minus. So now delta Cp of the reaction will be products minus the reactants. And product there is 1 mole, which is phi r by 2, minus reactants you have 2 times of phi r by 2. So that's why it will become minus phi r by 2. So delta Cp of the reaction is minus 5 r by 2. Okay. Well, we got this here. And now you notice that delta H2 is equal to delta H1 plus delta Cp into delta T. And now this delta H1 is equal to minus EA plus delta Cp of the reaction into T2 minus T1. Okay. So therefore delta H2 is equal to minus EA plus 5 by 2 RT. Got it? Everybody understood how we use that as an application here? So I suppose you got an idea how it is, used in electron gain enthalpy as well as ionization. Okay. Now let me get back to that equation where we were discussing. So here, so you can see this is what I have been used. So delta H of the reaction here at temperature T2, so T2 temperature will be equal to, or simply write it as 2. Delta H naught 2 will be equal to delta H naught 1 plus delta Cp of the reaction. Okay. So like that you can get delta G of the reaction two times. I mean, one will be delta G naught 2 and delta G naught 1. The difference of that two will be delta G of the reaction. Okay. Clear? Now, let us understand the next important term about pure substances. Okay. This is Gibbs free energy of pure substances. Well, what does that exactly mean? Let's try to figure out that. Check. Delta G, I mean, if I consider a pure substance and suppose it is following Gibbs function, which means I can say any small change in its free energy accounts for a small change in entropy, enthalpy, and small change in stored energy, which is Ts. Okay. Now, H can be represented as U plus PV. This is what we learned in enthalpy's definition. So, if there is any small change in enthalpy, it accounts for small change in internal energy and small change in PV energy. And U can also be written as Q plus W as per thermodynamics first law. So, small change in internal energy accounts for small amount of heat provided and small amount of work done. And work done, dW, as a general formula, what we can write is, minus PdV if there is an expansion. But is it necessary always expansion is the only way the work done can happen? Not necessary. Pure substances can also have work done without any expansion also. That means you can have two factors of work done. One is an expansion work done. The other one is a non-expansion work done. So when I write dW, here I can write it as minus PdV, which accounts for expansion work done, and dWNE. NE means non-expansion work done. Okay. Now let me substitute all of these points here. So instead of du, I'm substituting these values, dq minus pdv and non-expansion work, which I have written it here. And then d of pv can be written as minus pdv plus vdp, correct? D of pv can be written as vdp and pdv. Okay. And then you have d of ts. D of ts can be written as tds minus sdt. TDS minus SDT. And lastly, I'll carry the non-expansive work here. So you can clearly notice that TDS will get cancelled. PDV will get cancelled. What is remaining? DG is equal to VDP minus SDT plus non-expansion work. Okay. This is for non-expansion work. Clear? So from here we can say at constant temperature and pressure, you can see these two terms will get cancelled. So at constant temperature and pressure, dq will be equal to dWNE, and Ne means what? Non-expansive work. dW non-expansive work. So this is dg. Okay, clear? I think this part is understood. So if it is about ideal gases or any other system where non-expansive work is not there, acha, where do you see non-expansive work? Best example, chemical cells. Okay, if you see batteries, in batteries chemical reaction is happening, and that chemical reaction is actually making that reaction is releasing energy which is used as a work done. Correct? We are able to listen to music, so that energy is being transferred into a work. Clear? We are able to see cars keep moving due to batteries running, so wheels are moving, so work is being done again. Correct? So where are we using it from? We are using from the source of battery. But is the volume of the battery increasing or decreasing? No, that is constant. And temperature and pressure remains constant. In that particular unit, we are not changing temperature and pressure conditions. So at constant temperature and pressure, whatever the work that is happening from the battery is nothing but its free energy change. Clear, everybody? And that is what this accounts to. So non-expansive work. But let's say if we are talking about simple ideal gases, real gases, or anything like solids and liquids, where the non-expansive work is irrelevant, in that case, for a reversible process at constant temperature and pressure, dg will be equal to 0. Okay, change in free energy of the pure substances will be equal to 0. Understood? Now, where exactly, I mean, first, instead of directly doing this question, let me do one thing. I'll add one more page here and try to explain you how exactly we can use that, and I'll get back to that question again. Okay, let me derive it for case to case, and then I'll do that question more easily. Okay, check. Suppose if I'm talking about an isothermal case. Okay, suppose we have an isothermal case, which means there is no change in temperature. Okay, and what did we see? Delta G's general formula, we saw that VDP minus SDT plus non-expansive work done, dw, non-expansive work done. And since we are talking about ideal gases, real gases, so non-expansive work done is 0. So dg is mainly vdp minus sdt. Okay, and at constant temperature this factor will also become 0, so dg will be simply equal to vdp. This will be vdp. So that implies we can write it this way: dou g by dou p, dou g by dou p at constant temperature will always give you volume of a pure substance. Important. Volume of a pure substance, volume of pure substance will be always equal to dou g by dou p at constant temperature. Okay. Next case. This is for isothermal case. Within isothermal case also we can have it for ideal gas, we can have it for solids and liquids and so on. Okay. So within this case, let me write it as case 1 if it is for solids and liquids. Solids and liquids. For solids and liquids, we know that volume remains constant, right? So volume will remain constant. So therefore, dg will be equal to vdp here. And since volume is constant, if at all I integrate this dg from something like, g1 to g2 here, dg from g1 to g2 here, so that will be equal to volume is constant into p1 to p2 into dp. So that is equal to delta G of a substance, uh, change in free energy of a substance can be written as volume of the substance multiplied by P2 minus P1. Pressure it is kept at minus P1. Okay. This is about dG or delta G of a substance. In this case, here only, let me write down parallelly what is case 2. Case 2 is for ideal gas. For an ideal gas, volume is not constant, right, beta? Volume is always represented as nRT by P. You can write this as nRT by P. So therefore, dg can be written as integral P1 to P2, okay, nRT by P into dP. And since it is at constant temperature, nRT will come out and you'll get ln P2 by P1. You'll get this as ln P2 by P1. Okay. Ah, right. Here, everybody. Next, if it is, this is the first case. Now let me show you the next case, which is isobaric case. Suppose if it is isobaric process. Isobaric process means delta P is constant, so there is no change in the pressure. Okay, I mean delta P is 0, sorry. P is constant and delta P is 0. So we know that dg, which is equal to vdp minus sdt. Okay, considering non-expansive work is not there, then pressure is 0 here, so it is minus sdt. Dg will be equal to minus sdt. So from here we can get dg by dt, sorry, dou g by dou t, right, at constant pressure is equal to minus s. So you can see entropy of a pure substance, entropy of a pure substance can always be represented as change in free energy with respect to temperature at constant pressure. This is how we can represent it. Clear? Now, these graphs I have already, for this, the supportive graphs, I have already kept it here. So let me pull them up here. And let me explain these graphs as well. See, notice these two graphs. First, variation of Gibbs free energy for a pure substance. Okay. Now, if you're operating for a constant temperature, at a constant temperature, how does it vary? Just now we looked at, and this is for ideal gas. This is for ideal gas, and this is for, right, this is for um, solids and liquids. Solids and liquids. Okay, not delta P, VdP. Now notice this one. Free energy with respect to pressure, how does it vary? Okay, as the pressure increases or decreases. First, check out for solids. Okay, so we can say that because if you compare the solids, liquids, and gases, who would have more volume? Because it is directly proportional to the volume factor here. Okay, so usually at solids, you will always have a lower volume. So if you notice at a constant pressure term here, so gases must have a higher uh, free energy, and that's what these graphs will represent. Okay, so for gases, always these free energy would be at the higher value compared to liquid, compared to solids at a particular pressure. Okay, and same way between liquids to solids, also liquids has to have greater than that of solids. Okay, and you know that this is like y is equal to mx kind of a profile, which means it is passing through the origin like this. All right, so for solids and liquids, this is how the graph varies, and you will notice that uh, liquid will be higher than the solid form here. Now, if you do it at constant pressure, what it will learn? Variation of a pure substance with a temperature at a constant pressure. Okay, so this is variation of Gibbs free energy, with respect to temperature, okay, at constant pressure. So based on this, what we can say from here, we can say if it comes to entropy, because this delta G factor is actually representing the entropy here. Delta G, as the temperature changes, what is representing is entropy of the factor. And you know that for gases, the entropy is higher as compared to that of liquids, as compared to that of solids, isn't it? So that's why you will see, we generally know that gases, entropy of gas is greater than, much greater than liquids, which is greater than solids. Use this fundamental here, because S is greater here. So gases usually have steep value like this, because it's a negative value. Yeah, minus S, right? Minus S, as in, you can see as the temperature decreases, the entropy factor, free energy factor increases. Okay, because it has a higher entropy. Then liquids, which will go almost like this. For solids, you'll hardly see, hardly have much noticeable change. Okay. Clear, everybody? Okay. Now let me take you through this question. See, this was a JE question. JE asked 2-3 times the same question. Once it was asked in mains, and 2 times it was asked in advance. Same question, but variation in terms of values. But the idea is exactly same. See, what it was asked is like this: density of graphite and diamond were given. Okay, density of graphite and diamond were given, and delta G naught formation of diamond is given 2900 joules per mole. Calculate equilibrium pressure for conversion of graphite to diamond at 25 degrees Celsius. Okay. So how do we do this? See, we are trying to convert graphite into diamond. Okay. And you know that graphite is a standard condition of, the elemental form of carbon. It is the elemental form of carbon. So any formation values will be zero. That means delta H naught of formation is zero. Delta G naught formation is zero. Delta S naught formation is zero. For elemental form of, standard elemental form of pure substance. So this is a pure substance and elemental form will be zero. And for this delta G naught value is zero. For this delta G naught value is not zero. It is given 2900. So this will be 2900 minus 0. So what will be delta G of the reaction? It will be 2900. Correct? Is this point clear? Now we know that dg is equal to vdp. This part is not there. SDT is not there here. Now I can say if there is any change in the reaction. So how do we write the G here, beta? G is products minus reactant, correct? So basically I can write it as, okay, G of product is G of diamond minus G of graphite. G of graphite. This is delta G of the reaction, correct? And D of delta G of the reaction is what we are trying to predict with respect to pressure, how it is changing. Because when the pressure is changed, this delta G value will change. And delta G value will be equal to, delta G value will be, D of delta G will be equal to, how much is the volume delta V into dP. Okay. Because what is delta V now? Delta V is diamond minus graphite. Okay. So you can see dg C of diamond and dg C of graphite is equal to Vg of dP and Vd of dP. So if I take delta D of delta G of the reaction, it will be dg of diamond minus dg of graphite. So dg will be written as because dP is a common factor, I can write Vd minus Vg. Vd minus Vg is what? Volume change between graphite and diamond. Okay. Is this part clear, everybody? And now we are supposed to calculate per mole because we are trying to figure out, delta G naught only. So in that case, I can write for 1 mole, see. So for 1 mole, what we can write? dG of the reaction from delta G1 to delta G2, delta naught G2, this will be equal to 1 bar, because when the chemical reaction, when that reaction is given at formation conditions, that means we are supposed to maintain the pressure at 1 bar. From 1 bar, you have to take it to some new pressure, right, to get the change what we are looking into, right? So at this pressure, when it is reaching, it will reach to an equilibrium. So we are trying to figure out an equilibrium pressure at which graphite and diamond can coexist. So at this equilibrium pressure, delta G naught 2 value will be 0. So 0 minus delta G naught 1 is equal to delta V. Delta V can be written as mass of 1 mole. 1 mole of carbon is 12 divided by its density. So this is graphite, diamond minus this is graphite, 12 by this. So this is the volume of diamond, this is the volume of graphite into equilibrium pressure minus 1. And here this value was already given, minus 2900, and 12 by 3.51, 12 by 2.51 into P minus 1. Okay. And P minus 1 is in bar unit. How do I convert into Newton per meter square? You know that 1 bar unit is equal to 10 raised to power of 5 Newton per meter square, or pascals, 10 raised to power of 5 pascals. And that's why I multiplied it with 10 raised to power of 5. Okay. And 2900, if you notice, what is it given in? It is given in joules per mole, right? So this is already given in joules. So I don't have to change anything. So directly, if at all I take it to the other end, clear, and calculate what is the pressure, it is coming as 1.52 into 10 raised to power of 6 pascals. Everybody understood? Just based on unit conversion, this is what you will get. Any doubt with the reaction here? Any doubt with the solving here? This I told you already. Now coming to this one. For a chemical reaction ABCD, right? In the next topic, we'll be discussing something about equilibrium constant. Okay. And if you're expressing an equilibrium constant in terms of their pressures, we call it as Kp. So Kp is equal to pressures of the products minus pressures of the, product of the pressures. So Pc raised to power of C, Pd raised to power of D, Pa raised to power of A, and Pb raised to power of B. This is how we define Kp. Well, we haven't studied that yet, but as of now, remember it like a formula. So Kp is a constant value defined based on the equilibrium pressures of the products divided by equilibrium pressures of the reactants. Okay. And what about delta G of the reaction? Delta G of the reaction can be written as the product's free energy minus reactant's free energy. Correct. And if I write individually delta G at a constant temperature, what we can write? So let me write on that. Here I have written it. At constant temperature, we can write it as dgc is equal to Vc into dP plus D into Vd into dP, A into Va into dP, B into Vp into dP. Okay. And Vc can be written as RT by Pc for 1 mole. And here also I can write it as RT by Pd, RT by Pa, and RT by Pb. Correct. And now you can see this CRT is coming common, DRT is coming out here, ART is coming out here, and BRT is coming out here. Okay, clear? And integral of this entire thing. So what do I get? Integral of 1 by PC into DP will be equal to, PC by P naught C. This PC means equilibrium pressure divided by some P naught C, initial pressure. So same goes with PD by P naught D, PA by P naught A, and ln PB by P naught B. And if I take this RT common in all of them, and then make this C to go in the power places here. Let it go to the power places here. So I'll get ln RT ln PC raised to power of C, PD raised to power of D by PA raised to power of A and PB raised to power of C minus ln of P naught C raised to power of C, P naught D raised to power of D, and this entire thing. Now this value, right, is the pressure at any time. Okay, pressure at any time. What is the value? This is the generic pressures. And that is what we call it as, just like how we define Kp here, but this is only at equilibrium pressures. If it is not at equilibrium, then we call it as Qp. Qp means reaction quotient. Qp here represent reaction quotient. So reaction quotient is a value at any particular time, not necessarily equilibrium. So ln Qp minus this entire thing. Okay. So this value ln Q is equal to, if I multiply this RT ln Qp minus RT ln this entire thing. So this entire thing RT ln this one, this is what we define, this is what I define it as delta G naught. Okay, so what I got here is delta G is equal to, this entire thing is delta G naught. This entire thing is delta G naught plus RT ln Qp. Okay, and at equilibrium, you see that at equilibrium, what will happen? At equilibrium, this delta G will be equal to 0. When this is equal to 0, then Qp is equal to Kp. So basically, this entire thing is nothing but Kp. Okay, and this is what I have defined. Delta G naught is equal to minus RT ln Kp. Okay, honestly speaking, you will be directly using this formula, nothing to do with derivation. Okay, so delta G is equal to delta G naught plus RT ln Qp. Okay, and Qp, if it becomes Kp, then delta G will become 0, and this is the formula you will get. Delta G naught is equal to minus RT ln Kp. Okay. Now notice, if Kp value is 1, then delta G naught value will be negative. What does this mean? It means the reaction is spontaneous at standard conditions. So at standard conditions, if at all I give A, B, C, D, then AB will react to form CD and CD will not react to form AB. The reverse will not happen, forward reaction will happen if Kp is greater than 1. Next, if Kp is less than 1, that means the backward will happen, the forward will not happen. So it is spontaneous in backward direction, but non-spontaneous in forward direction. Okay. And for any chemical reaction, if delta G is 0, that means delta G naught may or may not be 0. Okay. To explain this in a simple terms, let me show you this part. Imagine like this. I have, you know, uh, a box here. I have a box here. A box as in a closed enclosure here. So which has N2 gas, H2 gas, and ammonia gas. All of them are maintained at a partial pressure of 1 bar. 1 bar is maintained. Temperature is maintained at a standard conditions, which is 25 degrees Celsius. Temperature, standard conditions, 25 degrees Celsius. Okay. At these conditions, let's see, if you have N2 plus 3H2 is giving 2NH3. Suppose if this reaction takes place, you can see this is 1 bar pressure, this is 1 bar pressure, and this is 1 bar pressure. Correct? Now tell me, if there is no reaction happening, then what does that mean? The Kp value in this case, suppose to reach the equilibrium, because initially we have 1 mole, 1 mole, and 1 mole. Now I can say that if it is 1 minus x and 1 minus 3x and it is 1 plus 2x, can I say that Kp value will be greater than 1? Because you can see product's value is greater than 1. reactants value is less than 1 because reactants will be in the denominator. That will increase the value of Kp. So Kp will be greater than 1, which implies delta G naught value is less than 1, implies spontaneous in forward direction. This is what I'm trying to tell you. Okay. Now, I took the same conditions this time. Again, I took the same box here, but these are not at standard conditions now. So that means it is at some temperature. Let's say this is at some temperature T kelvins. Now, nitrogen I took it as 5 bar. Okay, hydrogen I took it as 1 bar, and ammonia, there is no ammonia only. Let's say there is no ammonia here. Ammonia is 0 bar. Sorry, ammonia is 0 bar. Okay, so in that case, if this is 0, like this, it is 5 bar, 5 bar, 1 bar, and 0. So from here, 5 minus x, 1 minus 3x, and 2x. This is how if it is forming and it reaches an equilibrium. And let's say it has reached equilibrium now. At equilibrium, delta G value will be 0 because now these are not at standard conditions. Now you do not write it as naught. You will simply write it as delta G. So delta G is 0. And what is the formula we learned? Delta G is equal to delta G naught plus RT ln Q. So at equilibrium, delta G will be equal to 0 and QP will become Kp. So that implies delta G naught will be equal to minus RT ln Kp. Okay. Now it depends upon Kp value. So you can notice that delta G naught value may be negative or positive. It does not matter. That depends upon Kp value. But at non-standard conditions, if you are acquiring equilibrium, that means delta G naught value is not 0, but delta G value is 0. This is what I'm trying to explain out of these two graphs. If anybody has a doubt understanding what is delta G and delta G naught, please let me know right away. So start with this question, everybody. Try it on your own. So see the first one. What will be change in molar Gibbs free energy of H2O liquid at 300 kelvins. Okay, 300 kelvins, constant temperature. So temperature is constant. Clear? If compressed, from 10 bar to 20 bar, 10 bar to 20 bar. Got it? So just to give you a hint, it is H2O liquid is getting compressed to become H2O liquid at two different pressures. One is at 10 bar, one is at 20 bar. Got it? So in such case, you need to figure out what is delta G. Got it? So I want you to do this once. I'll give you 1 minute's time, then I'll discuss it. See, delta G is VdP minus SdT. You know that this factor will become 0 because you are operating at constant temperature. So that is equal to volume V, which is constant, into P2 minus P1. And how do I express volume? Volume is mass by density. So M by D into P2 minus P1. You know that for water, the density is almost one, the density is 1 and mass is 18 grams. So 18 by 1 into pressure. Pressure is 20 minus 10. But I need to express that in kgs, so into 10 raised to power of minus 3. Okay. But whatever the delta G which you are getting is in bar and liter. This is bar liter. But I want to express that in joules. So what do I get? Delta G is equal to 18 into 10 into 10 raised to power of minus 3 into 100. Why? Because 1 bar liter is equal to 100 joules. So it is joules per mole. Therefore, delta G will be equal to 18 joules per mole. That's how you get the value. Clear? Right. Start checking out the second question now, everybody. Sorry. Right. Notice the next question here. 1 mole of helium, correct? 300 kelvins, 10 atm is heated through a process in which pressure is directly proportional to temperature, right? So one thing, square of temperature. So P is directly proportional to T square. Okay. So that implies I can write P1 by P2 at two different pressures. I can write it as T1 by T2 whole square. Correct. So from here I can write P2 is equal to P1 multiplied by T2 by T1 whole square. This is how I can relate with P2. Now can I calculate that P2 here? P1 is given as 10. Temperature, uh, it is starting with 300. Now it has reached to 600. So that raised to power of 2. Okay. So that brings it 40. 40 atm. So basically from 10 atm, it has gone to 40 atm. Let me remind you what is the formula for delta S, of a system will be equal to NCV ln T2 by T1 plus NR ln V2 by V1. This is the formula which we know. Okay. Now here the temperature is also changing, volume, pressure, all of them are changing. So in that case, can I write, there are two ways you can solve it directly, or you can calculate first the volume here. See, V2 by V1 can be written as, uh, let me first write down the formula here. PV is equal to nRT, you know that. So volume is directly proportional to T by P. So that means V1 by V2 or V2 by V1 will be equal to T2 by P2 multiplied by P1 by T1. Correct? This is what you will have. So use that here. So V2 by V1 is equal to T2 by T1. T2 by T1 is 2 into P1 by P2. P1 is how much? P1 is 10 divided by 40. So how much we are getting? 1 by 2. So please check that the volume ratio V2 by V1 is coming out to be 1 by 2. Okay. And this is a helium. Helium is a monoatomic gas. For monoatomic gas, Cp value is 3R by 2. And how many moles? 1 mole is being used. So 1 into 3 by 2R into ln 2 plus again it is 1 into R ln V2 by V1, which is 1 by 2. Is 1 by 2. So that is equal to 3 by 2R, correct? ln2 minus R ln2, because that value ln2 is coming out to be common factor here. So 3 by 2 minus 1 into r ln 2. So that is equal to 1 by 2 r ln 2. This is the value you should get, and this is the answer given. Okay, this was a multiple correct question. This is how it was given, r ln 2 by 2. So please check it out. I hope all of you got that right. Now check out the next question, how it is been framed. Okay, for a chemical reaction, for a reaction, for a reaction where CO2 gas plus graphite is being heated together to convert into carbon monoxide. Delta H of the reaction is given 170 kilojoules. Delta S of the reaction is given 170 kilojoules. Sorry, joules per Kelvin. Okay. Now, the question asked is the reaction will be spontaneous, is spontaneous at what temperature? Option A is given as 300 kelvins, B is given as 1000 kelvins, C is given as 1100 kelvins, and D is given as 900 kelvins. Okay, this is what you need to check. Easy one. Please do solve it and check. Correct, Samay. That's right. So we just need to check out this delta G is equal to delta H minus T delta S. Okay. If it has to be spontaneous, this factor has to be less than 0. So delta H has to be less than delta T delta S. So T has to be greater than delta H by delta S. So which is equal to T is greater than delta H is how much? It is 170 into 1000 divided by 170. Got it? Isn't it? So which means how much we are getting here? Sorry, into 1000. So we're getting it as 1000 Kelvin. So temperature has to be greater than 1000, not 1000, but it has to be greater than 1000. Just be careful about that. So it has to be C. Okay, correct. Pratisha, right? Utsa, correct. Let's do the next one, beta. See, for perfectly for perfectly uh, crystalline solid, for perfectly crystalline solid, CPM value was given as AT cube plus BT, where ABR ABR constants, ABR constants, and if CPM is 0.4 joules per Kelvin, joules per Kelvin at 10 kelvins and 0.92 joules per kelvins, you know, uh, mole at 20 kelvins. Okay, here also there is mole. I forgot this many mole at 20 kelvins. Then molar entropy then molar entropy at 20 kelvins is how much? This is what we need to calculate. Molar entropy at 20 kelvins is how much? This is what we need to find. So the first step itself is a hint. For perfectly crystalline solid, entropy at 0 kelvins is 0. Done. Please check. See, delta S of the uh, delta S of temperature T, that is at 20 kelvins, will be equal to S at 20 minus S at 0 kelvins, correct? And S at 20 can be written as N into, okay, CPM into dt. Clear? From T1 to T2 minus 0, because for entropy at 0 kelvins will be equal to 0, isn't it? So therefore this is equal to N into integral 0 to 20. Cp is AT cube plus BT into dt. Correct? This is what I'm supposed to do, isn't it? So how do we get that? So what are the values given here? CP value is given, one at 10K, the other one at 20K. Clear? So at 10K and 20K, if CP is given, from there can we calculate A and B? That is the first thing we need to do. So that is 0.4 is equal to A into 10K, 10 raised to power of cube, plus B into 10. This is equation 1. And 0.92 is equal to A into 20 cube plus B into 20. This is equation 2. Correct? So when you work out A and B, once you get A and B, now you just need to substitute that values here and integrate. So, and since you are doing it for molar entropy, that means N value is 1 and 0 to 20. So this is basically A times of, you know, T raised to power of, 4 with T raised to power of 4. Clear? From 0 to 20 by 4. Okay, plus b times of t square by 2, 0 to 20. So after you get the value of a and b, a by 4 into t raised to power of 20 raised to power of 4, correct, minus b by 2 into 20 raised to power of 2. This is what you need to do. Clear? And solving everything, I'll just directly write the values. We are getting it as 0.813, sorry, 813 joules per mole per Kelvin. This is what I'm getting. Got it? Next, these are very simple objective type questions which has been asked. That is, find the sign of, find the sign of delta G, delta S, and delta G for the following. First, PCl5 plus 79 kilojoules per mole, that is giving PCl3 gas plus Cl2 gas. This is how it is given. Next, second one, clear? C solid plus half of O2, correct, is giving CO2 gas. Clear? This is giving CO2 gas. Third one, okay, calcium carbonate on tree plus 700 kilojoules per mole, that is giving calcium oxide plus carbon dioxide gas. And lastly, N2 gas plus 3H2 gas is giving 2NH3 gas, right, plus 180 kilojoules per mole. This is how the equations are given. So just watching these equations and the given information, we should be able to comment on the sign of delta H, delta S, and delta G. Okay. Check out the first one. In the first one, you will notice that if at all I have 79 been added, the added means energy being absorbed. Energy being taken means delta H of the reaction is greater than 0. It is endothermic. Energy has been taken up. Okay. And delta Ng, that is number of moles of products minus reactants of gaseous moles. Moles are greater than 0. That means it is products minus reactant is greater than 0 here. So which implies entropy of the overall reaction is increasing. So now what about delta G? Delta G is equal to delta H minus T delta S. So if this is positive and if this is positive, what would happen? This is positive and this is positive. It can be, have two cases now. If temperature increases, or I can say if temperature is greater than certain equilibrium temperature, then delta G will be less than 0. And if temperature is less than certain equilibrium temperature, then delta G will be greater than 0. This is the sign you need to identify. Got it? Similarly, look into the second case. In the second case, what we can say, you know that this is a combustion reaction. That's why the heat is been not given. You should realize that it is a combustion reaction. For a combustion reaction, delta H of the reaction is anyway going to be negative. It doesn't have to be shown. You should know that. And delta S of the reaction, if you notice that there is 1 mole here and there is half a mole here. So which means delta Ng, sorry, this is not half mole, 1 mole only, no? 1 into 1. So delta Ng is almost equal to 0. So which means delta S value will also be equal to 0. So delta G, which is equal to delta H minus T delta S. Since this factor is almost 0, so it depends on delta G will also be less than 0. Okay, this is the factor for second one. See the third one now. So if it comes to calcium carbonate, right? Again, energy is being utilized here or absorbed here. So delta H of the reaction is greater than 0. Delta Ng value is greater than 0 because gaseous moles are there on the product, not on the reactant side. So which means delta S of the reaction is also greater than 0. It is pretty much the first case only. Whatever we got the first case, that is the same thing here also. So copy, paste here, done. This is what we got. The third one is the same case. Okay. And what is the fourth case? Fourth case is here energy is shown it on the products, which means delta H is negative. It is an exothermic reaction. And what about delta Ng? Delta Ng is less than 0 because product are only 2, reactants are 4. So which means delta S of the reaction in this case will be less than 0. And delta G, which is equal to delta H minus T delta S here. So this is negative, this is negative. So again it becomes conditional. If temperature, correct, exceeds an equilibrium temperature, then delta G will be positive. If temperature is less than an equilibrium temperature, then delta G will be negative. So please look into the cases, everybody. Done, everybody? Okay, so we'll stop it here.